Hi guys, so my presentation is called 1001 Ways to Die. And just a bit about me, my name is Yaniv and I work as a security researcher at Checkpoint Software Technologies. During my day job I practice mainly malware research and vulnerability research. So that practically means that I spend most of my day staring at assembly code and binary codes and hex dumps and all kinds of other fun things like that. Although I couldn't quite find any to-dos inside the binary file yet, but I have something to look forward for. Anyway, during all the years I've been doing reverse engineering, there seems to be one problem that seems to be popping up again and again, and it's really irritating me, and I have to deal with it at least tens or maybe even hundreds times a day. And I'm sure you all share the same problem as me, and you all get to encounter it as well. And this problem is that, when we're doing reverse engineering, then basically we have two main methods, right? So we have static analysis, and for static analysis, we just open our binary file inside some kind of disassembler, whether it's IDA, Hopper, Rudder, or whatever you prefer. And we actually have a lot of information in there. I mean, those tools are really evolved quite well, throughout the years. And for me personally, if I could, I would never leave my IDA screen. I will do all my reverse engineering session just within my IDA because I feel so comfortable with it. But however, that's very rarely the case. I mean, at most times we have to resort to the help of debuggers because, well, static analysis tools, they have like an integral problem with them because, they are static and they just lack all the dynamic data. So how many times have you been faced with this problem, that you're doing some kind of static analysis, you get to some function call, and you just wish you would know the value of the argument passed to this function. Because, well, you could theoretically do it yourself and trace it back. It would just take you a lot of time, and it will be much easier to just look at the values at the debugger. So what you do is go to another screen, open a debugger, put the binary file in it, place the right breakpoints, hit those breakpoints, watch the raw values, and then all of a sudden you understand you're looking at some kind of struct. So again, you go back to your IDA screen, and you define this struct, and you go back to your debugger, and there's a lot of information going on back and forth from the static tools to the dynamic tools, and all of this is being passed mentally right through your heads. And that is very error-prone, I think. Well, as smart as we think we are and as good as we think we are, we can make mistakes here. And those mistakes can be revealed only much later on in the reversing session, and it could have catastrophic results. And the other thing is that it takes a lot of time, and it's really frustrating. I mean, for me, it takes all the fun out of reverse engineering because this is such a Sisyphic job that I would really like to have already inside my IDA screen. So it seems trivial to me that there should be some kind of solution to bridge this gap and bring us all the dynamic data right inside our IDA screens. Now, that's not a new problem, and I'm not the first one who's ever come up with this or who's come up with some kind of a solution. There's been numerous solutions in the past, and I like to categorize them to two main categories. One category is like standalone tools, and those standalone tools do a great job. But again, since they are standalone, then once I have to leave my disassembler screen and go to these tools, then again I have to mentally pass the data back and forth. And although they are really cool, they just don't solve the problem. They are just considered to me like next generation debuggers, and they don't solve this specific problem. The tools I'm talking about are actually IDA plugins that knows how to bring dynamic data right inside your IDA screen. And we're just, briefly going to go over two of the best solutions that I could find, and we're going to discuss the advantages and disadvantages of each one of them. So the first one is called IDA Splode. It was developed in 2014 by Zach Riegel, and for its dynamic framework, it uses the Intel PIN framework, which is a binary estimation, if you don't know. And so the thing is, it's really cool. You have to run your binary file inside PIN with a provided PIN tool, and then you get some kind of trace file which you later load into IDA, and then IDA Splode takes all this data and presents it to you. So that's really nice. And it has a very extensive tracing since it uses pin, and pin lets you put callback functions at a lot of interesting places in execution. So you can see all memory reads, writes, you can see function calls, function returns, you can see branch instructions. It's really cool. Another thing it gives you is branch statistics, like whenever you stand on any jump instruction, then you see how many times was this branch taken, how many times it wasn't taken. It's really insightful and it really helps you out. However, there are some cons about this, and one is that all data, as you've seen before, is stored inside your IDB file. Well, this could theoretically be fixed, but it's not fixed yet. And for me personally, I don't like other people touching my IDB file, let alone other plugins. And when I have so much data stored as comments inside my IDB file, I just can't find my hands and my legs, and I just throw this plugin away immediately. And another thing is that it only works on Intel-based architectures. Well, since PIN is Intel-based, it's designed by Intel. And another thing, as far as I could see, this tool is really good for and designed for Windows OS. So if you're looking into working with Linux or some other kind of OS, then you need to modify that accordingly, and it's not currently supported. So the other tool was actually presented here, if I'm not mistaken, last year. It's called FunCap. It was written in 2013 by a guy which name I'm not sure how to pronounce, Andrzej Dąbrowski. I hope I got it right. Sorry if I didn't. Anyway, for the dynamic framework, it actually uses IDA debugging API, and that seems to be really cool because you never have to leave your IDA screen. You just run a debugger, and whichever debugger is supported by IDA is also supported by FunCap. That's really cool. Now, what it does, it places breakpoints using the debugger at function calls and at function returns, and when those breakpoints are hit, it just gathers contexts. It tries to look at the argument values there. So that's how it looks like. And it's a very intuitive solution. I mean, it looks like a really simple solution, although it's not extensive as the other one because it only traces function calls and function returns. But I think that only, seeing function calls and function returns actually gives you a great insight about what this binary is doing. And that's like a good optimization of tracing algorithms, because if we actually want to trace everything, it would take forever. And another thing it does, it takes a step forward and tries to look at those arguments and see if they might be, ASCII or Unicode strings. And if they are, it just places the ASCII codes inside your IDB. So all of a sudden, inside your IDB, you see all kinds of registry keys, and IP addresses, and that's really cool. That's really a nice thing to have. Now, the cons about it that it doesn't really follow any new thread. So if your executable is creating any new thread, then FunCap will be completely blind to it. And that could be actually a problem when dealing with, almost every binary we're working with. And another thing is that argument offsets are actually calculated manually. So what it does, it goes to and looks at the value of ESP or RSP or whatever architecture we're talking about, and takes that, looks at how many arguments should be there, divides that by 4, and says, okay, so this should be the offset of the first argument, this is the second, this is the third. And this could work at a lot of cases, but of course, it could also not work at a lot of cases. And it seems to be like not the right thing to do, because all this data is actually already stored inside IDA, so why do I have to calculate it manually? It really makes it like not really usable. So, I was sitting down and thinking, I mean, those are obviously great tools, and why aren't a lot of people using them on a day-to-day basis? Because they really are there to solve a very, very important problem. So I tried to think of the reasons, and the ones I came up with is, first of all, as you've seen before, all the data that they bring from the debuggers or the whatever dynamic framework they're using is actually stored inside IDB. It's also stored inside text files in FunCap case, but still, it's not indexed. I can't do any cross-references between them. And it seems really logical, because there's a whole layer of logic that I can do on those raw values, and using these tools, I just simply can't do it because all I have is like text search, and that's really not enough. Now, another thing is that entry level for adding any custom functionality is relatively high. I mean, look at FunCap's case. They do string parsing. But if I wanted to do any other kind of parsing, that would be really difficult. I mean, I need to go over the code and do it myself. It might take me hours, days, maybe even weeks. But the thing is that the tool wasn't really designed for that. And, you know, everybody has its own parsing requirements. And it seems reasonable that there should be some kind of you know, something that will let me do that. Now, the most important point that I could think of is that both of these tools, or any of the tools that I could find, has any reference to value types. And what I mean by that, think about it. Funckup places breakpoints on function calls, then it goes and brings you the argument row value. But if this value is, for example, a struct, then what do I get? I only get the first member of this struct, and this is completely unusable to me because I actually want to see the entire struct. And what I have to do is open my debugger again and see the struct. And so why did I need this plugin in the first place? I mean, this types thing is the whole point of making this kind of plugins, in my opinion, at least. So I hope you are prepared to die. And so die is my plugin that I designed to solve this problem. And it's called there because it's a dynamic IDA enrichment framework. And what it does, it takes a very similar approach to the one Funckup did. It collects context from function calls and function returns. And once those raw values come back to me, I try to parse them in some kind of human-readable way. And that's the best definition I can find for it. And the other thing is that I tried to really design some kind of smart interaction between static and dynamic data. So you can move back and forth from static data to dynamic data and over again, and it could be very, very usable. And the last point is that I wanted to use as much IDA API magic as I could. I don't want to calculate anything myself, not the arguments, not their types, not their positions, nothing. I want all the data that is stored in IDA to be available to me and to use it inside my tool. So there are some implementation challenges here, and we're just briefly going to go over them. So the first one is, okay, so you want to collect function arguments and types and everything, but how exactly do you do it? I mean, IDA API is not exactly the most easy thing to read or to use. Another thing is, once we did manage to get those raw values, how do we parse them? Which parsers should we make? What is important? What isn't important? And another point is, okay, so let's say we could deal somehow with, you know, strings, booleans, or other easy types like that, but what do we do when we encounter structs, unions, references, I don't know, whatever complex types we have? So let's just try and answer those one by one, just quickly. So for function arguments, I had hours of fun with IDA API. It was really, I recommend it to everyone. Not really. Anyway, digging into it, I could find some kind of object called tinfot object, which is a type info object, and it holds a ridiculous amount of information about types. This is just a small screenshot of all the functions, of all its functionalities, and it's really cool. And the thing is that digging even deeper into this tinfot object, then I find those objects which are func type data t, func arg t, and arglog t, which actually gives me all the data about function arguments. I absolutely have everything in here. I mean, IDA tells me how many arguments does a function has. And when I know the arguments for a specific argument, it will tell me whether it was passed by stack, and if so, what's its offset, and whether it was passed by register, and if so, what's the register. And it tells me the type and the name of this argument, and it also tells me if this argument is guessed. I mean, if IDA doesn't know the type, then it just raises up the flag. And that's really cool. I can really use that inside my plugin. So the other thing is, now that I have the raw values, then how do I parse them? I mean, I have my own parsers, the one that I need for my work, but it's impossible to think of all the scenarios. So it really makes more sense to make some kind of plugin framework, which where anyone could write his own plugin and just plug it in the framework and start parsing his own values. So this all works something like this. You make up your logic, your parsing logic here, and your value parser gets two input arguments. One will be the argument type, and the other will be the actual value. Now, remember that this thing is actually running in runtime. So this has actual access to all memory at the point of execution. So the output will be some kind of human readable value, and you decide what is human readable value, and some kind of score. And I'll get to the score in a second. So let's look at an example. If, for example, we have a Boolean value, IDA tells us this is a Boolean value, and the value is the row value is 1, then we just output true and 10, because we are sure that this is a Boolean value because IDA knows so. But if IDA doesn't know the type, if it's guessed, then we can still say, hey, this is 1. So if it was a Boolean value, so the value will be true. However, I'm guessing, so the score is a bit lower. And you can set the scores however you like. It depends on your logic. So that's basically value parsers. And now for complex data types. So those value parsers could work really good when talking about, strings or Boolean values. But what we do when we get to those structs, unions, references, so that's pretty simple. We just break them up until we get to the simple types. So what does that mean? For structs and unions, we can use the same T info T object I showed you before to just enumerate all its members. And the same goes for arrays, and the same goes for references. We actually have a function to deal with all the dereferencing stuff. So we don't really have to do anything ourselves. Everything is already done within the IDA API. That's cool. So I prepared this nice illustration to show you how DI exactly works. So this is our IDA. And inside IDA, we have our disassembler, and we have our debugger. And on top of both of these, we have the IDA API, which lets us access everything, of course, as you've seen before. So now we have DI, and DI is a plugin for IDA. And it has is the DI core, which holds all the logic. And it also has two very important parts. One would be the value parsers. This is the plugin framework I was talking about. And another will be the IDB, where all the parsed values will be actually stored. So this is our example code here, okay? And we see a very simple code. There are two function calls, one to func1 and the other to an unknown function. Func1 gets two input arguments. One will be a string with the value str1, the other will be just the value 1. And the unknown function gets just one input argument. It's a string with, again, the value str1. The difference between the functions is that for function 1, IDA knows all the types. It has the symbols or derived them somehow, and it actually knows the types. For the unknown function, IDA knows nothing about. So let's see how it works. When you first start DI, the first thing that will happen that the disassembler will look for any call instructions inside the function you're currently standing on, and we place breakpoints on these functions, and then we hit the debugger. The debugger gets to the first function, and then we issue a step in command, and we step into that function. Now, once we've stepped into the function, we just start to take the function arguments. So using the disassembler, take the first argument, which is car star A, and this is now passed to the parser plugin framework. And since we know the type and the parsers know the type, so the string parser is pulled out and being used on this value. And the output of this will be str1, and str1 will be stored in the database. Now, the second argument is an integer, and it too will be passed to the value parsers. However, we don't have a parser for integer, so we just simply store the row value inside IDB. Now, after we did that, there's another thing we do, and that's walk through this function again for call instructions. And now we continue the debugging and get to string compare. Now, string compare is a library function, and for library function, it's like it's a case, you can either do this again and again inside library functions, and if we're talking about Windows, you probably end up in somewhere like NTDLL, but you don't have to do that. So that's a question. It's really configurable. You can choose whether you want to do it or not. If not, it will just go one step inside strcompare and give you all the arguments that it got, and that's it, go out. But whether or not we like to do it, let's just continue and say we got out of strcompare, and we're continuing execution, stepping out of the function. And once we've stepped out of the function and hit the main function, there's one more thing we need to do, which is to parse the return value. And again, we know it's a Boolean value, pass it to the value parsers, and enter true into the IDB. Now we get to the unknown function. So we step into the unknown function, and in this case, you see that the arguments are both int and int, so that's IDA's way of telling us that, hey, I don't know what the types are. But we have a better way to do it because we look at the T-info-T object and we actually see the flag. So when we take this argument now and pass it to the value parsers, they will know that this is a guessed type. So they have no way of pulling out the correct plugin, so they will just try all the plugins, and each plugin who can actually guess that value will do it. So in this case, first of all, we store the raw value inside IDB, and then the string parser will say, hey, that could be a string, so let's store that in IDB. And now it's up to you to choose which one is correct. You just look at the function call and say, hey, this can't be a raw value, this must be a string, and then you set the type as a string. So that's basically it. That's how DAI works. And now let's talk a bit about the value parsers. Now DAI will only be as good as its value parsers. I mean, as much value parsers there will be, as many values will parse, DAI will get better and better. And what you have to understand, what I did up till now, me and the small community that uses DAI, is just write up parsers for our specific needs. And whenever we got to something we need to parse, then we just wrote a parser for it. So let me show you what we have up till now. So let's start with the simple value parsers, which are string parser, as you've seen before. Now, in here, we actually use the IDC get string, which helps us to parse ASCII strings, Unicode strings, Pascal strings, and a whole other bunch of strings that I really don't know anything about, but we do parse them. Boolean parser, as you've seen, 1 is true, 0 is false, pretty easy. Another thing is a function parser. So when we get a raw value, this parser actually checks if that raw value references any beginning of function. And if it does, it will actually give you the function name. So when a function is being passed as an argument to another function, instead of seeing the raw value, we'll actually see the function name, which is really useful. And the other thing is a module parser, which just does the same thing, only with modules. So if kernel32, for example, will be passed as an argument to a function, then we will see the string kernel32, and we will know that it's a module, so it will be really easy to work like that. So a bit more advanced parsers is the handle parser. Now, we wrote this parser to handle Windows handles, and it works only on local debugger, but it could theoretically work on the remote ones. And what it does, it takes the raw value, and it uses duplicate handle to try and duplicate it, and if it succeeds, it uses anti-query object to get the handle type and name. So think about it, it's really cool. I can actually see all the runtime handles. So when a function is passed a handle, I can see that handle, what's its type, and what's its name. That's really super useful. And this is also another good example of a parser, which is std string. I came up with a malware that uses std strings. I don't know why. It's the first one I saw, and I really didn't. I wasn't so familiar with the implementation of std strings, which is like basic string. So for those of you who are too unfamiliar with it, that's like how basic string works. I mean, at offset 4 of this complex object, there's a union, which holds 3 members. One is a buffer, the other is a pointer, and the string can be either stored at a buffer as string, or it can be stored as a pointer to a string. So offset 4 either stores the string or the offsets to a string. And why is that? I mean, I'm not really sure if it's genius or stupid. Anyway, that's how it works. And when we're debugging this, it really makes our life hard, because whenever we get a basic string, we have to go to this offset and check, is it a string? Hey, is it a reference? And it takes a lot of time. So writing a parser for this is actually pretty easy. We don't need to know anything, almost anything about the implementation. We just go to this offset 4 and see, hey, is this a string? Cool. If not, is this a reference to a string? Cool. Then we have a basic string. One more thing we have to note is that, if offset 4 is a string, then we might also want to check that offset 0 is not a string. We're just looking at the substring there. But if we just implement this logic, then we have a parser for basic strings, and all of a sudden we can see all runtime executed basic strings. So that's basically it. And I'm kind of finished talking, and I have 3 demos for you of DAI. I chose these demos really, really carefully, and they are from different worlds in the reverse engineering. So let's just go to the first one. So the first one is actually another research project that I'm working on. And during this project, I came up with this application. It's an A10 firmware upgrade utility, and it has some kind of password protection, very stupid password protection in it. And we need to bypass that, and we need to do it quickly. So the thing is that when opening this in IDA, this code is a really ugly C++ code, and I actually did it without DAI, and it took me, and I'm pretty experienced, it took me about 15 minutes to get to the point where I could bypass this protection. Now, 15 minutes. Now, look at how quickly can I do it with DAI. So praying to the demo gods that everything will work. Yeah. So this is the utility. It looks something like this. Can you see well? Yeah, that's a password. So I enter some kind of password here and hit OK. And yeah, of course, it's an invalid password. And that's what we have to bypass. So let's load it up in IDA. OK, cool. It's loaded. And now DAI is also loaded. And the first thing you notice when you load DAI, an IDA with a DAI plugin, is this nice skull ASCII art, which is really one of the best features we have. And then you will notice this little menu here, which says DAI. And opening it up, you will see all kinds of options, like to load a previously stored DAIDB or to save your DAIDB, and settings about, and we're quickly going to go over all of them. So in the settings one, you actually see that you have here the option to step into system libraries, which I told you before, and two other options that I'm going to show you in the next example. And all of these are practically used for debugging. It means whether you want to actually parse arrays, containers, which are structs and unions, dereferences, arguments, or whatever. The two values at the top of the screen are actually used for optimization. So maximal function calls means that when DAI will encounter the same function that's been executed more than this amount of time, it will stop monitoring it. So it's really useful when talking about like UI cases where the functions were executed like thousands of times and you don't really care about their values, so you just exclude them by doing this. And the other thing is the max dereference depth, because we must have some kind of, to stop somewhere when dereferencing stuff. Otherwise, we will never stop, probably. So that's basically it. It's pretty simple. And this is our program. And we have three options to start DAI. One will be to debug a custom scope. And that means that we can just choose to debug somewhere between this function and this function. We can actually choose functions, and that will be the only scope being debugged. And another thing is that we could debug the entire code, and that means before we even start execution, we browse through the entire code and we'll place breakpoints on each call instruction. That could be a bit slower. And the other thing is just the example that I showed you, which is go from current location. So we just want to start, in this case, from winmain, because we don't care about all the CRCT stuff and everything that's going on before winmain. So let's just stand on winmain here and hit Alt-F, which is the shortcut, and DAI will start. So this takes a while, but remember that it took me like 15 minutes before. So it's loading up, hopefully. Okay, cool. We got this screen. This is the password. So let's just enter, any password. Let's say recon2015. It's a bit slow because don't forget it's now actually tracing everything in the background. So that's it, recon2015. Let's hit OK here and see what happens. Maybe it's the password. Yeah, no, it's not. Cool. So that's it. Now the application stops. I'm thrown out, and everything returns to normal. Now, DAI has two main views. One is the function view, and the other is the value view. So let's start by looking at the function view. So function view will now give you this nice screen here, showing you all the functions being executed at runtime. So all of these functions have actually been executed, and this is the number of times they've been actually seen. So let's take a look at the first one. Also, if you have any threads, then you can see them here. In this case, we just have a single thread, but you can, split it up by thread or see all the threads. So the first one will be AFX get file by name, and it's been called right here. This is the point in the code when it's been called. So if we double click that, we can see that, hey, that's where it's been called. See? Cool. So when we open that, we can see occurrence 0 because, for each point in the code where there's a call instruction, it could be called several times, for instance, if it's like inside some kind of loop. So for this instance, we just have one occurrence. And when we open it up, we can actually see all the, let me go here. Sorry. So we can actually see all the arguments being passed to this function. This is a string. Its name is LP string 1, Imax length, and these are the call values. These are the values that were present at function call, and the other one shows you all the values that are present when the function returned. So if it changed, you can see the change, and that's pretty much it. Now for this function, we did know the symbols. As you see, we know all the names and everything, but let's say for the other function, right here, you see all the values are written as int because we don't really know them, and die places this ugly question mark just right near them, which means that these are actually guessed. I mean, the value parsers actually guessed those values, and look, we can see everything. I mean, it makes sense that it passed, you know, a string value, a Boolean value, another like string value, and the return argument down there is true. So it's Boolean, so it really helps us a lot. And just some more nice features before I go on. For instance, if you stand here on this occurrence and just right-click it, you can actually see a call graph showing you the exact path of execution that led up to this function, which could come in really handy sometimes. And let's just browse down here a bit until we get to, where is it? Ah, there it is. WSA startup, a very known function. Let's open it up. And we see this function now, and it has 3 elements: word, LPWS data, and then integer. And this LPWS data is actually a complex data type, and that's a pointer. And if we open it up, then we dereference it, and we find that we hit a struct. And when we open that struct up, then we actually see all the members of the struct and all their values. So we actually just, you know, took a look at all this struct data at runtime. And that's really cool. That could be really, really helpful, in my opinion. So, okay, so that was the function view. You have a couple of more options, like show CFG will show you the entire CFG. It's totally clickable, so if you want to, you know, go into one function, but if it helps you. And we have another thing that will like mark and unmark execution flow, so we can actually mark the functions being executed, which could come in handy, and we can, of course, take it off if we want. So the other view I've been talking about is called value view. Now, value view will give you a totally different view of the execution. You will not see the functions, but you will actually see the parsed values here. So those are all the parsed values that I have encountered during the execution. And you can filter them out by, you know, just looking, let's see all the modules being executed. So there's been only one module here, and you see its row value was, yeah, okay. And instead of just showing you the row value, you actually see the module name. So this could be really helpful. And same goes for functions, for example. Here we have a lot of functions. And also, same goes for strings. And now for strings, if you remember, it was quite a long time ago, but I entered recon2015 as the password, yeah? So let's look up if we can see recon2015 here. If you see it, tell me. Ah, here it is. So here you see, recon2015. So we actually saw that value because we entered it at runtime. And what we can do now is just double-click this value, and boom, we hit a function where that value was actually entered. And let's look at which function it is. Hey, it's strcompare. And which is the what is the other argument being passed here? Well, it's A10-2015-0620, which might be the password, right? So let's just look at this. Here's strcompare, you see? And now I actually have the password. So do you remember it? Because I keep forgetting the password. What was it? So A10-2015-0620. So let's just do this. A10-2015-0620. And boom, we just bypassed the password protection. It just took me like 2 minutes to do this instead of 15 minutes. Think about how useful can this be. So that was my first example. I have 2 more. No. Back to the presentation. And second one. Okay, so the second one is actually a feature I didn't talk to you about. I consider it like a side feature of DAI, but the thing is that, when we're reversing like C++ code, for example, then we got a lot of indirect calls and vtables and all this other kind of stuff that makes our life really hard. Now, the thing is that when DAI works, so when it steps into a function, so it makes sense that we can look back at where we came from and say, hey, was there any xref coming from there? And if not, we can just place it because we know we just came from there. So by just doing this, we just solved all indirect calls, because every indirect call will now have an integrated xref into the place it's being called. And another thing we do is that when we step into a function, we check whether this function is actually defined or not defined. And if it's not defined, we can try and define it. So whenever we have some kind of undefined blobs inside our IDA, then when simply using DAI without even using any value parsers, then we can actually get a complete code analysis, or not complete, but more complete than it was before. So let's just see how we do that. So the application, as I said or didn't say, it's 7-zip CLI. I've been doing a bit of work with that. And that's somewhere over here. Yep. So let's open it up in IDA. Does it open? The sculpting. Okay, cool. So can you see this good enough? Okay. So here I've set up a few pointers here to just show you what's going on with this application. So we have a couple of undefined functions and a couple of indirect calls, just to show you this. So let's step on this undefined function, and it's an undefined function. That's a function, and we don't have any xrefs to this function, nothing at all. So we can define it ourselves, but let's not do that. We have a couple of those here, another one, and another one. Cool. Now we have a few indirect calls here. So let's just send on this indirect call, for example, and see, well, we don't have any xrefs, of course. And another one here. Let's stand here. Sorry. Yeah, again, no xrefs, nothing, absolutely nothing. So we just want to quickly solve these issues. So we just stand here, and now we go to DAI settings, and I told you before I would talk about, those are the two features that I mentioned. One is new function analysis, which will actually try to define the function. The other will be add xrefs if they are missing. So just by checking those two options and running DAI, let's see what happens. So the debugger is now started. It's taking a while. Okay, cool. That's it. It's done. Now let's look what happened. So the undefined function, yeah, it's now defined. See? And all their xrefs are here. Everything is cool. Let's look at the other ones. Another undefined function defined, and another undefined function also defined. Now, as for the indirect calls, let's go to the first indirect call. Where is it? Yeah, here it is. Let's stand on it, and Control J. Hey, now we have an xref, and we have an xref to this function. And when standing on this function and xrefing back, then hey, we now got a xref to an indirect call, which is pretty useful, I think. And same goes for this indirect call. Hey, here we go. Xref, cool. And the other one, somewhere over here. I think it's this one or this one. Cool. Yeah, pretty impressive, no? Thank you. Okay, so now this is like where the demo gods really hit me, because I need IDA 64-bit to run this demo, and it seems like my IDA64B just crashed last night. So I do have a video presentation of it, and I can try using another computer. Shift, would you like to try and hook it up? I hope it works. If not, I will show you the demo. Anyway, just a few words about this. Well, you didn't think I let you off here without doing any analyzing of any Trojan or malware. So this is going to be, yeah, take it off. So this is going to be the explosive Trojan. It's a Trojan that we've, malware campaign that we've just recently uncovered. And the thing here is that, you know, once we have the IDB, that's not the end of it. I mean, there's a whole lot of logic we can actually implement on the database itself. So we can just, it works? Ah, I can't believe it, it didn't work before. Cool, cool, okay. So there's a whole lot of logic we can implement on the database itself. I mean, just, you know, think about the usages on automated tools and stuff like that. Now, let me see what I did here, I don't know. Let's start it again. Whoa, that's really small. Okay, so this is I just have the IDB file here, and I'm not going to run the malware on my friend's machine. So what I'm going to do here, this is really small, huh? So I'm going to show you how I load a previously stored IDB. So I just go here and load IDB, and you know, choose my IDB, which is named DDB file accordingly. And it takes it a while, and it loads everything up. How can you guys see the output window in the back? Do you see it good enough? Not? I have a zoom it. I will try to zoom as much as I can. So was it loaded? Yeah, okay. Let me just, you know, take it up a bit. Okay, so that's what you see when you load the IDB. It says there were 449 functions loaded and parsed values and threads and whatever. So the thing is, our mission here now is to try and find this malware has some kind of deobfuscation function, a text deobfuscation function, which is very common for every malware. Now, our job here is to try and find that deobfuscation function using nothing but die, not even a bit of static analysis. So let's see how we do that. We've previously ran die and just loaded the IDB. So we do have some kind of API that lets you access all the IDB stuff. So, well, that's really, really, really small. So what I do now is just load up this API. So here it's imported into IDA. And next thing I'm going to do is, okay, so I give it a command to load up all functions that it has stored inside IDB. So how many functions do I have? Let's take a look. Len of functions. So as it said before, we now have 449 executed functions. So that's not enough. But since we're talking about the obfuscation function, then we would like to rule out all library functions out of this, you know, list, because obviously a deobfuscation function won't be a library function. So let's just, where's my cursor? Okay. Let's just take it out. And okay. So now I give it a command, and now I have the no-lib functions, which are just the data set without the library functions. So again, len of functions. Now I have only 158 functions. Still, not good enough. So what I want to do now is actually try and take out all the functions that I noticed are returning strings, because a deobfuscation function must return a string, right? So hitting this, okay, so now we have all of those functions. Now we're up with only 17 functions. Hey, that's great, right? But let's filter it out a bit more and say, okay, I want to see only the top 10 functions out of this, the one that was called the most, because obviously the deobfuscation function will be called a lot during execution, right? So now we have that filtered out, and just one more filter will be like to sort them out according to the amount of xrefs they have, because whether or not it was, you know, executed, still a deobfuscation function must have a lot of xrefs coming out from all over the code, whether or not it was executed. So now we have everything sorted here, and let's, where is it? Okay, so let's iterate through this and print it out. Cool. Now we're left only with these functions here, okay? One of those functions must be the deobfuscation function. At least we hope so. So let's take a look at the first one. It is, I hope I can find it. So let's open up function view here, our function view. Yeah, that's a problem. Let's put it up here. No, up here. Cool. So, whoa, this is really small. Even I can see it. Okay, just a second. I will zoom it in a second, okay? So this is the function we found. This is the first one that was returned. You see down here. Let's look at its occurrences and see what it actually returned. So let me open up just a few of those. So yeah. This doesn't really look like a deobfuscation function, right? So this question mark thing is the actual return value, and it can be a deobfuscation function because it just returns gibberish. So that's not it. That's not it. So if we actually go to this function implementation, this is my actual IDB file. So we can see that this is a get substring function, okay, which actually matches all of these parameters that I've just said. So it makes sense that it will be the first one. But let's look at the second one. Let me just load it up in function view. Function view. Ah, cool. So it's supposed to be somewhere in here. D97. Looking it up. Yeah, here it is. Cool. Let's open up some of the occurrences here. So 1 occurrence, 2 occurrence, 3 occurrence, 4 occurrence, 5 occurrence. Can you see it? We get this kind of, what looks like a base 64 on the wrong way, and the output values are actually strings, and those are actually the obfuscated strings. So here we just found them. We did absolutely nothing. That would take me in reversing session like at least about half an hour to get to that, and I just did it now practically automatically. So that's really, really useful when doing malware research, I think. And that's my third presentation. I hope you like it. Let me just try and switch back to my presentation. Just a few more slides left. Where is it? I just threw it down here, no? Okay, so I got to do the demos. It was really fun. So a few things that we still have to do in doing DAI, and one of them is handling tank functions. Now, tank functions actually break up all our logic, because for a tank function, what happens is that when we step into a function, we just have a series of instructions that end up in some kind of jump instruction. So we don't actually place the breakpoint at the call instruction, and that will be absolutely blind to whatever is going on there. And there are ways for IDA to know tank functions. It actually flags them, but it doesn't know about all tank functions, and we have to find some kind of solution to that. So have that in mind when using DAI. Another thing is complex function parsers, because what we do now is just take the function arguments and parse them one by one. But that could be not a necessary case. There could be another case when we would like to take the value of one argument and use that value as an input to another argument. Like if we're talking about, we have some kind of size argument, and then we want to pass that size to another argument, then this must be implemented in some kind of a complex function parser. So the other thing is better GUI. Well, I'm not really your genius GUI guy, and I did it as best as I could, and I really struggled with this Qt thing, let me tell you. But it's working, and if somebody wants, is really good with Qt and wants to design a new GUI, then please feel free to approach me and tell me about it. Another thing is a much better database, because I'm also not your database guy, and I just did what I could. And another thing is to solve some very dramatic crashes that we're experiencing here and there. And we actually have a case open with Hextrace about that, and we really hope we can fix that. But if anyone can somehow replicate this issue or come up with good examples of crashes, then please let me know about it, and we'll pass that through to Hextrace. And otherwise, you've seen it's working. It's just here and there that there are crashes. And so it looks cool. Can you have it? Yes, you can. Ada is a completely open source tool, and you can find it at my GitHub page, which was just made public today. Write it down. And really, the most important point, and if you like it, then please contribute. Write your own parsers, take them up into the GitHub page, and enrich the community. And just one more thing I have to say before I finish is Sark. This is actually a framework made by my colleague Tamir Bahar, and it's really making life much easier when working with IDA Python. I recommend you all to try this thing because IDA Python can be, and IDA API can be quite complex at sometimes. So it's really cool. I really recommend it. That's it, guys. That's the answer. Any questions? Thank you.
Hey, very cool. Hey, I have just one quick question on this.
Where are you?
I don't know if I should just come up there. It's kind of hectic at the moment. But in my experience, IDA has a hard time with functions that pass arguments via registers, right? Like this call, fast call. It won't pick those up a lot of the time. Is DI, because of its dynamic analysis, is it easy for it to find those and resolve that?
No, I totally take all the values that I can from IDA. So if IDA fucks up, DI fucks up too.
Thank you.
That's it?
Hi.
Yeah,
I have a question for you. I have seen your entire presentation, and I was wondering if when you have done the last demo, you have run the tool in a virtual machine or not?
Yes, I did.
Okay.
Why?
It means that you have to install IDA in the infected test virtual machine, right?
You could use the remote IDA debugger. That could work. It just takes a lot of time. Usually, I just like to install my own IDA on the infected machine, but that's not necessary at all.
Okay, thank you.
More? No? Thanks, guys.